Okay, now moving on to the atomic nature of matter, right? So matter, you've probably seen enough physics and chemistry and so forth in the past to realize that matter in general is composed of atoms, right? So an atom is the smallest particle of an element that has all the element's chemical properties. So if I were to take hydrogen gas and split it up into smaller and smaller amounts, or if I were to take a piece of iron and cut it up, I would ultimately get to a part of the iron that's the smallest part, that I cannot divide it further and still preserve the properties of iron. I could take that thing that we call an atom and cut it up further, but then I take the atom, it behaves like iron. Now I cut it up, now I get protons and neutrons and electrons, but they don't individually behave like iron anymore, right? So that's the definition of an atom. So here is an example of an image taken by a scanning tunneling microscope at IBM, one of their labs, where what they did is on the surface of, you can see on a copper crystal surface, they put iron atoms. So they were actually able to, using a special technique with a scanning tunneling microscope, you take a probe and you lift one atom and you come and drop it here. Lift the next atom, come and drop it here. So using this, they actually created a corral. You can see that they took 48 iron atoms and put them in this ring, in a circle here, and they captured electron waves in here, if I recall correctly. Yeah, to corral electron waves. So you can see that these ripples are actually electrons behaving like waves, just like a pool and ripples on the pool, right? And what they did is the walls that they used to capture the electrons were made of iron atoms. So in the scanning tunneling microscope, each of these is a representation of the iron atom. This little cone thingy. So atomic nucleus is basically the core of the atom, which basically, what's the core, the insides of the atom? Okay, there isn't a periodic table in this room that oh, there is. Okay. So the core of the atom is basically the nucleus. The nucleus contains protons and neutrons, right? The proton is the positively charged particle in the nucleus. The neutron is neutral. And outside of this are the electrons. Let's see if I have a picture. Okay, there. So take an atom. In general, the atom kind of looks like this. You've probably all seen these pictures, right? Where at the very core of this tiny little nucleus, the nucleus has these very heavy particles, the protons and the neutrons. Look further out and you see the electrons. Here's an electron traveling in this orbit. Here's another electron traveling in that orbit. Here's another one in this orbit. So this is a two-dimensional representation. If you want to look a more three-dimensionally looking representation, here is that representation. Here's the core, the nucleus. Outside of this is a shell, right? Here's the yellow shell, and in the yellow shell you have the first two electrons that are whizzing around. Then you look further out, there's an area where there's no electrons, and then there's the next shell, and in this shell you can have up to 8 electrons and so on, right? So this is the Bohr model, or the shell electron, or the orbital model of the atom. If you look at the very core of the atom, the nucleus, it's composed of these particles, protons, which are positive, and neutrons, which are negative. The electrons are much smaller. Did I say negative? Thank you for catching that extra credit. The neutrons are neutral, not negative. The electrons are negative, right? So if you look at the atom, what happens is the nucleus, if you look at think of a football field, right? Soccer field, football field. At the very center of the football field, you take a football, so you're in the stadium, right? Take the football and place it in the center of the field. The atom, you can think of it as the size of the football field. The nucleus is the size of that football. So the atom is mostly empty space. So if you think of the atom as this room, what happens is the room is completely empty, and down here I probably have a little marble in the center, right? That marble is the nucleus, and everything else is empty space. Now at the periphery, the outside of the room, you end up having these electrons that are whizzing around. Now, in comparative size, I'm going to replace the marble with an elephant. Each elephant, like a proton is an elephant, a neutron is an elephant, right? You can think of them as neon green elephants and pink elephants. Pink for proton, neon, right? For neutron. Now, as you look further out, what happens is you have mice. There's a mouse that's whizzing around. You can pick any color you want for the mouse. Electron. What color starts with E?
Raccoon.
That's a good question. I've never thought of to see if there's a color that starts with E. Okay, so why would I go with E? Oh, that's right, because it's electron. Okay, so anyway, you got a mouse on the outside, right, running around in circles. In the center here are a collection of elephants, like all clustered together. This is the nucleus compared to the electron. So the atom is huge compared to the nucleus, and it's huge compared to the electrons. The electrons are really tiny compared to the protons or the neutrons. The ratio in mass is about 2,000 times. A neutron is approximately the same mass as a proton. An electron is 1/2000th the mass. So comparatively, it's like a mouse versus an elephant, right? So that's what's going on there. Now it turns out how this was discovered, the fact that there were different models for how the particles in an atom were believed to be. It was thought that the mass of the atom is spread throughout the atom, right? It was like a uniform, like a marble, like an atom is like a marble, was thought to be the case. And then another model was the pudding with raisins model, where there were raisins throughout the rice pudding or whatever, was another model for the atom. Finally, what ended up winning was this model, which said basically that here's the atom, and all the mass, 99.99% of the mass is concentrated in a very tiny little dot at the center of the atom. That dot is what we call the nucleus. How this was discovered was through this experiment. This is a piece of lead, a block of lead. You drill a hole in the lead, not all the way through, but part of the way through, and inside this you put some radioactive material. And then you have a cap over the top that's made of lead. Now when you want a beam of radioactivity, you remove the cap. So what happens is, the radioactive beam, in this case alpha particles are basically helium atoms without the electrons, come zooming out. These particles were then sent into a thin foil of gold. And then around this you had film, right? A big circular film around this, and you look to see what was happening. Now if the gold was totally solid, these helium atoms would come and hit the gold and just bounce off. So you'd end up with some random distribution of bounced off. It's like taking ping pong balls and throwing them at that wall. Throw them at the wall, and then you collect the ping pong balls. They come back, nothing makes it through, right? That's what you would expect if the gold was totally solid. However, instead of that, what happened is, here's what happened. Here's the helium atom going through the gold. It goes all the way through without any problem. Another one goes through, another one goes through. Some of them are deflected a little bit, right? And very rarely, a few of them are reflected back. So based on these proportions and the directions that they reflect back, you can tell, wow, look at this, 99% of the helium particles went right through the gold, as if the gold did not exist. A small fraction bounced back, as if they hit a very massive center. So based on that is how physicists came up with the model. Isn't
this the test that they used to sort of prove that quantum physics existed? I remember hearing something about this when I was, I don't know if I was watching something or reading something about quantum physics, but the way that the particles passed through the foil was different on separate occasions, and they determined that, perceptively you see this and this happens, and that was the test that sort of made them open their eyes to the matter. I don't know if I'm thinking the right thing, but it looks familiar.
It's an experiment that's similar to this, but not the same.
Right?
It's not the same experiment as this. It's one where what happens is, depending on the kind of experiment you set up, the electron behaves like a particle or like a wave.
Right. That's okay.
Right. So that is demonstrated the wave-particle duality.
Okay.
Beyond the scope of this lecture, but I think we may have quantum physics in the future in this course. Right. By the way, that's what I make my living at. The bulk of what I do is quantum mechanics, and I take electrons and I fling them at objects, and I fling them hard enough that what would normally be a particle converts into a wave, and then I look at the waves, electron waves interact with with matter, and then from that I can infer things about the matter and so on, right? So that is my area of expertise. It's my area. That's what I do for a living. Okay. Anyway, extra credit to you for the question, right? So this whole technique is called Rutherford backscattering. Okay, so an electron, the mouse, is the negatively charged particle in the atom. And so here's an application. That's weird. Here's an application where this is something called a cathode ray tube. I'll have to go back and see what's up with this. Okay, basically what happens is you have a plate of metal that is charged negative. So this is the source of electrons. And now here we have another wire coming down to another plate of metal that's charged positive. And what happens is, because this is inside a glass ampule or a glass tube that's evacuated, so you don't have air in it, electrons, now this red arrow is supposed to go from the center of this down through this hole. I have no idea why it moved, right? Probably got tired is my guess and kind of gave into the pressure of gravity.
There's no air in there.
Yes, but gravity I think is able to make it through. Okay, better, kind of. So electrons leave the negatively charged plate. They accelerate in this direction because of the charge. Then in the center of this plate is a little hole. So the bulk of the electrons that leave here are stopped by this plate and they go off into that circuit. But some of them make it through this hole, giving us an electron beam. This electron beam, we can then put a magnet here, and depending on the strength of the magnet and the position of the magnet, you can get this beam to switch from side to side, to deflect, right? You can deflect it this way and deflect it this way. This is exactly how cathode ray tubes work, right? A cathode ray tube, which is, think of all the old PC monitors as well as TVs, right? What will happen is you use this method to create an electron beam. So electrons are traveling this direction. You apply a magnetic field in this direction, which would deflect the beam like this. You apply a different magnetic field in this direction, which will deflect the beam like this. So by doing this, you can what's called rastering, right? You all know what rastering is? Nope. Okay, rastering is where, let's say that is your TV, that wall is your TV screen. You send the beam at that corner. Now you change the magnetic field to deflect the beam in a straight line all the way there. Then you deflect the beam down, then you raster it back, deflect it down, raster it back. And by doing this, you can paint the whole screen, right? You can cover the whole screen. Now let's say that you have little pixels of some chemical that gives off light when an electron hits it, right? So what happens is, let's say that the length of my, the length of my pointer is proportional to the beam, the intensity of the electron beam. So as I go to the very top of the room there, I have a longer beam. So you get a bright spot. As I move here, I change the length. I make it smaller. The next spot is dimmer. Now I put it off. So it's totally black. The next one, brighter, smaller, brighter, brighter, right? So by doing this, I can paint one line of pixels, bright, dark, medium, bright, dark, medium, and so on, right? So I paint one line, then I come back and I paint the next line, then I paint the next line, I paint the next line, and I do this all the way down to the bottom. And I do this really fast. By doing this, what?
I just can't imagine someone actually came up with this.
Isn't it amazing? See, this is why I'm totally fascinated by technology, right? So by doing this, and you do it really fast, what happens is you coat the glass with a phosphor, a chemical that will accept the electron and then give off light for a certain length of time. And you do it so that it doesn't totally die by the time I'm finished painting this screen. So by doing this, now I can paint a picture. I've just painted, in this case, it used to be green and white or a black and white picture on that, right? Next, what I do is I start painting the next screen. Then I paint the next screen. So one screen I paint it, then 1/60th of a second later I paint the next screen. Then 1/60th of a second later I paint the next screen. So if I paint this at roughly 60 frames, if you call it, per second, I can create a movie for you by changing the pixels slightly. So here's a dog running across. Isn't that amazing? And all of that comes out of this simple idea of having a charged plate, electrons traveling from here to here, they move over here and it comes through, right? I find the whole field of technology completely fascinating. I mean, that's why I enjoy being in it. Okay, let's go ahead and stop the lecture here so that you can start the lab, right? And then, because one of my commitments to you is to end the lectures a bit early on Monday to give us more time with the labs.